So when we last left off, we discussed carbonyl addition reactions. We looked at the Wolff-Kishner reduction reaction and the Wittig reaction, which are two useful methods, both for one for the reduction of carbonyls, and the second is a wonderful method to prepare alkenes directly from carbonyls with stereo control. What we're now going to talk about are reactions involving carbonyl carbons and the positions adjacent to carbonyl carbons. So it's important that we establish some nomenclature first. For carbon position, Greek letters are used to indicate the position of substituents with a carbon atom adjacent or bonded to the carbonyl carbon being labeled as the alpha carbon. So alpha followed by beta, gamma, and delta. This nomenclature is used to refer to carbon positions relative to a carbonyl. The alpha position is particularly important when we talk about enolate chemistry, while the beta position is particularly important when we talk about conjugate addition reactions. Does this common nomenclature make sense to everyone?
Could you repeat the letters again?
So alpha is the position directly adjacent to the carbonyl. Beta is the position adjacent to the alpha position. Gamma is after beta, and delta is after gamma. Does that make sense? Did that clarify? Any other questions I can address on carbon position? Okay, so let's keep going now. And let's talk about conjugate nucleophilic addition to unsaturated aldehydes and ketones. So conjugated aldehydes, ketones, and conjugated carbonyls in general contain two electrophilic sites. The carbonyl carbon, right? We know the carbonyl carbon is electrophilic. I mean, we can even draw out the resonance structure where we can clearly see a partial positive charge on the carbonyl carbon. Further, the alkene beta carbon is also electrophilic. And as a result, unsaturated ketones, aldehydes, and other carbonyls have two sites of reactivity, the beta position or the carbonyl carbon position. So when unsaturated or conjugated ketones and aldehydes react with nucleophiles, we have to consider and think about which site gets attacked by our nucleophile. And it depends on the sterics and electronic character of our nucleophile. Does this initial idea make sense? Unsaturated ketones and aldehydes have two sites of reactivity. Now, nucleophiles can add to either site. Let's talk about a mechanism that we are familiar with. Typical nucleophilic addition directly to the carbonyl carbon is called 1,2 addition. We see this all the time when we have Grignard reagents and other quote unquote hard nucleophiles, where our electron density is highly localized on a single atom in our nucleophile. So an example of 1,2 addition would be addition of a Grignard reagent into a carbonyl. For example, if you have this cyclohexyl ketone and you treat it with ethyl magnesium bromide, you'd be able to cleanly isolate the 1,2 addition product. Does this make sense to everyone? Is everyone comfortable with the mechanism for 1,2 addition? Any questions? Okay, let's keep going then. And let's talk about a new pathway for reactivity, a new mechanism when we have an unsaturated aldehyde or ketone. The nucleophile can also add to the carbon-carbon double bond of an unsaturated aldehyde or ketone via a conjugate addition or 1,4 addition mechanism, in which case the nucleophile attacks the beta position and we kick our electron density in this carbon-carbon double bond to the adjacent carbon-carbon single bond. This breaks our carbon-oxygen double bond, and in turn, we generate an enolate. Enolates are quite important carbon-centered nucleophiles that we'll talk about a lot in later chapters. So 1,4 addition is not just a method to form bonds between a carbon and a nucleophile. It's also a method to prepare enolates, which can be used for further reactions. Does this mechanism of 1,4 addition make sense to everyone? Any questions on this mechanism? Okay. Now, one thing that I'd like you to note, without a carbonyl or another resonance electron withdrawing group, the carbon-carbon double bond would not be activated for nucleophilic attack. You don't see the reaction or the direct reaction of strong nucleophiles with isolated alkenes. If you wanted to functionalize that alkene, you would have to use a different set of reagents. Does everyone see how only activated alkenes react with nucleophiles? Does that idea make sense? Any questions on this idea? Now, just to make sure we're paying attention here, is this alkene considered activated under this definition? I see a lot of students typing no. Would you be able to provide a reason why? So why is this alkene not considered activated? Let's try to explain and justify our explanation. The phenyl is not electron withdrawing. Exactly right. Yep, perfect. So let's look now at one example of conjugate addition, which is the conjugate addition of amines. Now, when you have primary and secondary amines, these primary and secondary amines add to alpha beta unsaturated aldehydes and ketones to yield beta amino aldehydes and ketones. So why no tertiary? Why are tertiary amines not viable? Well, let's think about what happens. After addition, we'd end up with the following addition product. So if we have a tertiary amine and it adds in a 1,4 fashion, what's the problem here? Why aren't we able to isolate the addition product when you have a tertiary amine? What do we notice about this tertiary amine? Is it a good or bad leaving group? What do we think? Does that tertiary amine, which is now a quaternary ammonium salt after addition, does that nitrogen look like a good leaving group? Or is it tolerable? What do we think? Does this addition product that I have drawn for a tertiary amine look stable? What do we think? Does anyone have a comment or perspective to share? So we noted that primary and secondary amines add to unsaturated aldehydes and ketones. Tertiary amines, however, do not efficiently react. We looked at this addition product and we noticed that after addition, we end up with this ammonium salt. Does this look like a good leaving group? Let's just answer that. Does this nitrogen look like a good leaving group as drawn? So it has a positive charge, right? Ammonium salts are generally quite efficient leaving groups. So as a result, we just as easily want to kick down our lone pair and kick out this tertiary amine nucleophile. This is a great leaving group. So it's always important when you read through the substrates for a reaction that you think about why are certain substrates not allowed. Does that explanation make sense to everyone? Does everyone see why tertiary amines are not very good for this reaction? Does everyone see why a tertiary amine is not an effective nucleophile for conjugate addition? Okay, so let's talk about this reaction. First and foremost, it's reversible and it's under thermodynamic control. Rather than observing the imine product, we exclusively observe the beta aminoketone. Mechanistically, this occurs via attack of our amine on the beta position. This generates our enolate. And from here, we have a series of proton transfers to get a neutral isolable product. From here, we're able to cleanly isolate a beta aminoketone. Now, one thing that's important to note, this addition is reversible and treatment with base or acid and heat can regenerate the conjugated ketone or aldehyde. So addition of amines to make a beta aminoketone can serve as a method to temporarily protect this unsaturated alkene and this alkene that's conjugated to our ketone. Does this mechanism make sense? Okay, let's keep going now and let's try to apply what we've learned and let's try to predict the product of the following reaction and draw a mechanism for this reaction. So this time, rather than using a nitrogen-centered nucleophile, we're going to use a sulfur-centered nucleophile. Sulfur-centered nucleophiles, nitrogen-centered nucleophiles are great nucleophiles for 1,4 addition because they're quote unquote soft nucleophiles. Generally, if your nucleophile is not an enolate, well, generally, if your nucleophile is not a carbon-centered anion, it will generally be a soft nucleophile and prefer to add 1,4 in most cases. So let's take a few moments. Let's take about 3 to 4 minutes to look over this problem. And let's try to draw out a reasonable mechanism for this reaction, predict the products from this reaction. And if you have any questions, don't be shy to share them in the chat or verbally. And if you have any proposed responses, you can share them in the chat, verbally, or using the annotate tool on the class whiteboard. It's attached. This is known as sodium thiophenolate, and the structure looks like this. It's a soft sulfur-centered nucleophile, which is wonderful for 1,4 addition. So, does anyone have a proposal for the mechanism for this reaction? Or would anyone like to share their proposed mechanism in the chat, verbally, or on the class whiteboard? I'd really want to have us practice drawing out the mechanisms for these reactions, and I'd like to see if you have any questions, so that way I can provide some input and feedback. So, would anyone like to share their proposed mechanism? Or is there a question that I can address as you're working through this mechanism? Yep, in typical 1,4 addition fashion, the sulfur nucleophile will attack the beta position and generate an enolate. So from here, now that we have this enolate, if we treat an enolate, which is a basic species, with acid, what happens in the second step? So now that we have an enolate, which is a basic species, under acidic conditions, when we treat an enolate with acid, we will protonate that enolate, and that gives us our isolable addition product. Perfect, perfect. Yep, this student proposed mechanism looks perfectly reasonable. So let me clear the student annotations and just redraw, so that way we can have everything referenced in our final class note set. Okay, so the first step, we're under basic conditions. We have a strong nucleophile. Sulfur-centered nucleophiles are soft nucleophiles and prefer to add in a 1,4 addition pattern. That in turn gives us our resulting enolate. Treatment with acid protonates our enolate, You just have to be careful not to use too much acid, or you may get reversion back to the conjugated ketone. That in turn gives us our isolable 1,4 addition product. Does this mechanism make sense to everyone? Any questions? Any questions on this mechanism? It's 1,4 addition. In that the nucleophilic attack occurs at the beta position. Does that make sense? So this is the site of reactivity for 1,4 addition, while 1,2 addition attacks the carbonyl carbon.
Oh, so we count oxygen as like number 1?
Yep, exactly.
Okay, I see.
Any other questions I can address? Okay, so let's keep going then. So one thing to note is if you work under basic conditions, just like we saw in the previous example, we're able to generate an enolate. And this enolate can be leveraged for further reactions. This numbering convention is the typical convention for assigning where the nucleophile attacks for conjugated and normal carbonyls. So 1,2 addition and 1,4 addition are common terminologies. Sorry, what was the question? What happened to the double bond in the last problem? So in this case, this enolate can be directly protonated. And in this case, the electron density in that enolate gets protonated off. So we've essentially used the electron density in this double bond to form a carbon-hydrogen bond. Does that answer your question? Perfect. So under basic conditions, a enolate is generated, and that enolate can be used for further reactions, and we'll see a lot of that in later chapters. One pretty common thing that can be done is the enolate can be trapped with trimethyl chloride or used for reaction with other electrophiles. So for example, if we have an enolate generated from conjugate addition, we can treat it with trimethyl chloride and in turn isolate the protected enolate. So this is a way to generate an isolable enolate equivalent that can be used for further reactions. Does this idea make sense to everyone? Any questions on this idea? Okay, let's keep going now and let's talk about another class of soft nucleophile, which are organocopper reagents. So organolithium or Grignard reagents are quite useful for 1,2 addition, but not so much for 1,4 addition. Reaction of an alpha beta unsaturated ketone with an organocuprate nucleophiles is useful for 1,4 addition of alkyl groups. So this is a useful method to install and form a carbon-carbon bond at the beta position or the 4 position. Typically, a lithium diorganocopper reagent, otherwise known as a Gilman reagent, is used. And these Gilman reagents are prepared by reaction of 1 equivalent of cuprous iodide with 2 equivalents of organolithium. So not the most atom efficient method, but it's very useful for getting the desired chemoselectivity. So Gilman reagents are considered soft nucleophiles, and they preferentially add via the 1,4 addition pattern. Grignard reagents are hard nucleophiles and prefer to add in a 1,2 fashion. One important side feature of Gilman reagents is that these organocuprate reagents, these Gilman reagents, are effective nucleophiles for SN2 reactions, where if you try to do an SN2 reaction with a Grignard, you're going to get a very low yield of your desired product, and you'll see a lot of byproducts, including elimination. Does this idea make sense to everyone? Does everyone understand the key difference in chemoselectivity between Grignards and Gilman reagents? Okay, so then let's keep going. Let's keep going. And let's take a look. Yes, Grignard reagents and organolithium reagents prefer to add 1,2, while Gilman reagents prefer to add 1,4. That is correct. So to provide you a mechanism, so your Gilman reagent, which is a diorganocuprate species, first your Gilman reagent, which can be thought of where the copper is our nucleophilic atom. Our Gilman reagent attacks our beta position that in turn generates our enolate, and then the enolate is then protonated with acid during the workup. So this is a wonderful method to form carbon-carbon bonds at the beta position. So another mechanism proposed for the addition of Gilman reagents entails attack of your Gilman reagent at the beta position. You generate this alkyl cuprate species. And then from here, you have almost a reductive elimination step where we form a carbon-carbon bond and we generate this organocopper byproduct. I like this second mechanism more because it really shows why Gilman reagents are softer nucleophiles. Because rather than having a hard carbon-centered nucleophile, we instead have this copper-centered nucleophile. And copper, similar to sulfur and nitrogen, is generally a softer nucleophile and thus favors addition at the beta position. Does this make sense? Yeah, so it's really can be best thought of as a copper-centered nucleophile that adds, and then there's a reductive elimination step where copper is reduced and we form a carbon-carbon bond. This arrow pushing step here is known as reductive elimination. And this is a common mechanistic step in many reactions involving organometallic species. Any other questions on this mechanism? Okay, let's keep going. In this case, I'd like you to predict the product of the following reaction and draw a mechanism for the following reaction. So in this first case, we have a Grignard reagent reacting with an unsaturated carbonyl. What product will we observe and why? So let's take about 3 to 4 minutes to work through this example. And I'd like students to share any questions that they have or their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. So we have a lot of students noting that Grignard reagents, they're hard carbon-centered nucleophiles, and as such, they attack directly in a 1-2 fashion to the carbonyl carbon. Perfect. Would you be able to draw the product from that addition reaction? Yep, exactly right. Perfect. So the key thing to note, Grignard reagents prefer to add 1-2, and this difference in regioselectivity is important because depending on your choice of reagent, you'll either see the 1-2 or 1-4 addition product. So let's clear these student responses and let's annotate this mechanism just for our instructor key. Okay, so we know Grignard reagents prefer to add 1-2 over 1-4. So our Grignard reagent, in this case phenyl, magnesium bromide, will prefer to attack directly at the carbonyl carbon to yield our addition product. And then of course, if we treat with H3O plus or acid to quench our generated alkoxide ion, we would get an isolable tertiary alcohol. Does this mechanism make sense to everyone? It's not the alkoxide isn't necessarily insoluble. It's just you're not going to isolate the alkoxide salt directly. It's easier to isolate the alcohol. Did that answer your question? Perfect. Okay, so let's keep going now. And we have the same substrate, but this time we're treating it with a Gilman reagent. So in this case, we have this organocuprate reagent. So let's take about 3 to 4 minutes. And if you have any questions as you work through this problem, don't be shy to ask those questions in the chat or verbally. And then I'd like students to share their proposed responses in the chat, verbally, or using the annotate tool. So are there any questions that I can address, or does anyone have a proposed mechanism that they'd like to share? So we have a lot of students commenting copper, like most Gilman reagents, prefers to attack 1,4. Okay. Would someone like to draw out that conjugate addition mechanism? Would anyone like to share their proposed mechanism on the class whiteboard? So would anyone like to try to annotate out the proposed mechanism for this organocuprate addition? Yep. So our organocuprate will attack 1,4. And then what happens next? We're making an enolate species. What do we get after this addition? Would we be able to draw out the product from this addition step?
What does the copper molecule look like?
Oh, so this organocuprate is just copper with two, in this case, 2 N-propyl groups. So it looks something like this. And this is an organocuprate rather than organocopper. So when we have 2 alkyl groups bonded to our copper atom, this is known as an organocuprate, while 1 alkyl group is known as an organocopper. And the reason why the organocuprate is more reactive stems from the fact that after addition, your copper is not as good of a leaving group as if you have an organocopper species adding. Did that answer your question?
Yes.
Perfect. So from here, we have our alkyl copper species. So from here, how do we form our desired carbon-carbon bond? What's the key step? Now that we have this alkyl copper species, how do we form our desired carbon-carbon bond? Would anyone like to show that final reductive elimination step? So in this case, we want to form this desired bond, right? And we need to break these two bonds, right? So let's draw out the arrow pushing mechanism to complete that. Yep, very close. So in this case, we would draw it out. So let's redraw this mechanism momentarily, and we'll talk about the reductive elimination step. So the class correctly noted that organocuprate reagents are soft nucleophiles that prefer to attack and add in a 1,4 fashion. Now that we have our alkyl copper species, for our reductive elimination step, we form our key carbon-carbon bond and we break our carbon-copper bond. And that in turn gives us our desired 1,4 addition product. Does this mechanism make sense to everyone? So the key thing that I'd like you to note is that Grignard reagents prefer to add 1,2. Soft nucleophiles, such as organocuprate reagents, prefer to add 1,4. Any questions on this example and the mechanism for conjugate addition of organocuprate reagents? Okay, let's keep going now. In terms of predicting regioselectivity for 1,2 versus 1,4 addition, hard nucleophiles such as Grignards or organolithium reagents prefer to add 1,2. Soft nucleophiles such as organocuprates, thiols, and enolates prefer to add 1,4. If you'd like more reading that's typically addressed in higher level organic classes, you may want to look over hard, soft, acid, base theory that's typically covered in upper division organic courses. Generally, if it's not a Grignard or organolithium, it's going to prefer to add 1,4. So we've finished chapter 20, and I'd
19.
like, oh, sorry, 19. And are there any last minute questions on this chapter before we archive today's recording? If not, we'll save today's recording, and next